Hello, welcome back. In this lecture, we are going to continue our discussion for chapter 16. We're going to discuss the first coding example, okay? And this example is about the binary search tree implementation using linked structure. And we have two files here. We have the binary search tree definition. We have the test driver. So first, let's take a look at the binary search tree. Okay, so we define the class, and it's generic, as we previously explained. This T must implement the comparable interface because the binary search tree strictly follows the ordering. Okay, so we need to keep that. And for the comparison and for generic reference, then the comparable interface is a necessary or comparator interface. Okay. So same thing for the bin node, we define it as a static inner class. So it has three parts: data and the left and the right child. Okay. And the constructor with parameters. So here we have the left and the right subtree. Okay. Okay. So this is the bin node definition. And if you recall, in binary search tree, we only have a single instance variable, root node. Okay, the type is a bin node. And for binary search tree, we start with a empty tree, so set root node to null. Okay, and if you have an item to be initiated for this tree, then you can set a root node, but you need to create the new bin node. Okay, so that's why here you call the bin nodes classes constructor to build it, and the left and right subtree are null. And to check if the binary search tree is empty, you just check the root node. And this is the search algorithm. The search method is the method you try to search an item. Okay, so our cursor start at the root node, and it's a bin node. And we also have this flag. And then we use this loop, while loop, okay? And be careful, we put the cursor null first, okay, to avoid the short circuit issue. So if it's not a null node, okay, then you compare. Okay, you call equal or compare to, is it? So if the item is equal, then you find the item. Okay, once you find the item, if the found is true, then the loop will be terminated. Okay, and then you can return it. And then compare. If it's less than, that is called compare to from the comparable interface, less than 0, then you go to left. So you set cursor equals cursor's left. So go to left. Otherwise, you go to the right. So pretty straightforward following our search algorithm. Okay. And we have another related method. We define for search, we call it a search tool, and we define it as private. And this is just a utility instance method that's going to be used for our other instance method. Okay, so it not just return true or false if item found, also going to keep track of the parent node, okay, and the current node itself. So it will keep track of that. Because if you remember later on, we are going to do the delete. Delete also needed to do search. Okay, so at that time we needed to use the search. So that's why over here we provide this utility function. So the root, the parent node, this is the parent node. We initially set it to root. This is a cursor current node. Okay, and the parent node initially set it to null. Okay, and then same thing, we are going to do the same, like the search, is it? So equal, less than, you go to left or go to right. But at the same time, you update the parent node, is it? So basically, it's parent equals cursor, is it? And then cursor equals cursors left or right. Okay, so we do this kind of pair upgrade, okay, to keep track of the parent node and the current node for this search. And we set this method as instance, private instance, so only within this class it accessible, okay. Outside it cannot be accessed. So that's a search to function. And then we have this insert, okay. So for insert, we also start at the root node. We also keep track of the parent node, okay. And the same thing over here. So this is kind of like the search you need to find, okay. And if it's already in the item already in the tree, so we are not going to do insert because the tree only support unique items. Otherwise, we are going to determine our insertion. As if a parent is null, then that means it's an empty tree. Yeah, so you need to set the root node. Otherwise, you need to find where you're going to insert to left or insert to right, is it? And we also keep track of the parent node, is it? So insert to the left, then parents left will be the new bin node. Okay, otherwise, parents right are going to be this new bin node. You also need to call the new, okay, because it's insert. Okay, so that's the insert operation. And then let's take a look at the delete operation. Okay. So for the delete, we try to delete the item. If you recall, we need to keep track of the current node and the parent node. Okay, so that's why here we have an array to keep track of. So here we are going to call the search to, okay, to see if we can find the item. If we cannot, then we just need to stop. Okay. If we can find, then we update. Okay, the current node and the parent node. Okay, and then we are going to say, okay, so this is the case that the node you're going to delete has both left and right child, not null, okay? Then what you need to do, if you recall, you need to find the next in order. The next in order go to right. Okay. At the same time, you also need to keep track of the parent node. Okay. And then you go to the left all the way, the furthest, until it's a it's null. That's it. You go all the way. Okay. At the same time, keep track of the parent node and the next in order. Okay. And after you find the next in order, okay, then we can swap the node you want to delete, the item you want to delete with the next in order with it. And also you put the item you want to find to the next in order. Okay, so we do the swap here. After the swap, then the code reduced to that to the either leaf node or a node with a single child case. Okay, then you see you can just uh, keep track of who is a child node. Okay, we also need to keep track of the child node because we needed to reconnect. If you recall, this is a parent. Is it? So parent. Something like so this is parent, okay, and this is a child node, okay, child node. So you want to delete this one, so you need to reconnect parent and the child. Okay, so that's why we also need to keep track of the child node, okay. And after this, then the case is going to be reduced. Is it if the root, if it is a root, you also need to update the root node, okay. And otherwise, it's reduced to the case, either left or the right. Okay, then you just reset the parent left or right connect with the child node. Okay, so that's about the delete operation. And next, let's take a look. How do we implement the depth first? First search, or search traversal. Okay, traversal. So we have in order, we have pre-order, post-order. Okay, so similar. So for in order, if you take a look, we just call auxiliary function. We call it in order auxiliary, and pass in with a root node. Okay, and within it, you can take a look. Is it so? Then it calls. So this is a recursive function. This is a recursive method. So it call itself, but with the left child. And here it calls itself with the right child. So in order it's visit left, and then here you output the node you're going to visit, is it? And then right. So left node and right. Okay. When you do left and right, you have the recursive call involved. Okay. So then it will take care of uh, the depth first traversal with in order. The output will be in ascending order. And similar, if you take a look, we have pre-order, it's similar, but if you take a look, for the pre-order is you visit node first. So node, then left and right. Okay, so post order, then you can see, you can find the same thing. It's left, right, and then node. So all similar concept, okay. So we implement the recursive function using the auxiliary function call. And for this one, and yeah, so over here we do the breath first. Mm, First traverse, okay. And so for this one, we need a queue, okay. So a queue in Java collections, it's an interface, so it's achieved through linked list, okay. So its type is being node for this queue. So you first add the root node, okay, so just a single node in the queue. And then you start to loop through the queue until it's empty. Okay, so, and we want to know the queue size, okay, for the node in at one level, is it at the specific level? and then you remove the item from the queue, At the same time, you're going to add. So this is the item you're going to add to the queue. Is it? Oh, this is the item that you removed. Okay, so you get the item out, display that. But we are going to include the left tree and the right tree if it exists. Okay, it's not empty, then you're going to include that. Okay. Yeah, and then you just keep doing the DQ. So remove item from the queue and output the contents, and at the same time add the left and the right node to the queue. Okay, so that's this binary search tree that we implemented. And then here we have the testing driver. Okay, for this testing driver, what we do is we first create an empty tree. Okay, then we fill the tree. We keep calling insert operation. Okay, we get off the data from a file. Okay, so here we are going to open a file, and it's a file, plain text file, pretty simple one. So it has a number of integers. So we're going to read off the integers and add them to the tree. Okay, so here we build the tree, build our binary search tree. Okay, then we are going to do the in-order traversal, pre-order traversal, and post-order traversal. Okay, do the recursive call for the traversal. And if you take a look, here is the output. Okay, so the in order, you can see, yeah, it's in ascending order. Is it pre-order? Yeah, root node is the first. And post order, yeah, root node is the last. And we also have a function to print out the tree. Okay, so here is text output of the tree. Okay. And then what next we are going to do is we are going to do the tree delete with a specific item. What we did, we tried to delete 64. Is it after we call it, we can double check. Is it if you take a look the output, yeah, the tree is 64 is deleted, if you see. Yeah, it's deleted from the tree. Okay. After that, what we did, we do the breadth first traversal, okay? And you can see, yeah, here is a breadth first traversal for the output. Okay, so that's the first coding example in this chapter. In the next lecture, we are going to go over the next one. See you.